we have already seen the statement of this theorem, but let's once more go through it. We have a polynomial px over the field f, and here we also have the assumption that f has all nth roots of unity for all positive integers n. So that assumption is there, and this px is solvable by radicals over f. Then the Galois group of this polynomial over f is a solvable group. So let's now see the proof. The proof starts by considering the splitting field of px over f. Let K be the splitting field of px over f. And then we are going to write the meaning of this, that px is solvable by radicals over f. Since px is solvable by radicals over f. So what does that mean? That means that there is a finite sequence of fields with these properties. There exists a sequence of fields like this. The first term of that sequence is the original base field, and then we obtain an extension of that by adjoining to f some element omega 1, and then we adjoin something to f1 to get another extension f2. Say we adjoin omega 2 to f2, and we continue like this. Eventually, we obtain the extension fk of the previous field in this sequence, fk minus 1, by adjoining some element omega k to it, such that some powers of these omega i's belong to the previous field. That means some power of omega 1 to the power r1 belongs to the previous field. It belongs to f. Similarly, some power of omega 2 belongs to f1, like that. Finally, some power of omega k belongs to f k minus 1, and the splitting field k is a subfield of this largest field in this sequence, that is fk. Okay. Now we are going to make an assumption about which we have already discussed before. So we assume, why this assumption can be legitimately made, we have already discussed this before, so I am not going to go into that again. We assume that without loss of generality, that this largest field fk is a normal extension of f, our base field. we assume that Fk is a normal extension of F. I mean, of course, Fk here in this sequence is maybe it's far away from F, but after all, this is also an extension of F ultimately, no? So it's a normal extension of F. So being a normal extension of F, Fk is also normal over any intermediate field. That is, if you have some field which is a subfield of Fk and is itself an extension of F, then Fk will be a normal extension of that intermediate field as well. In particular, for all these Fi's, Fk is a normal extension. So, Fk is a normal extension of each Fi in this sequence. All right. Now, next, what our author says is that each Fi is a normal extension of the previous field Fi minus 1. And this follows from lemma 573. The question is how? Let me first write by, so this is in another paragraph. Each Fi is a normal extension of Fi minus 1. For this, we have to recall lemma 573. It is that lemma in which we start with a field which has all the nth roots of unity for some n. So it was this that let F be a field which has all the nth roots of unity. Okay. Let A be a non-zero element in F, and let all the nth roots of unity for some positive integer n. That's understood. Okay, I'm not writing that again. And let K be the splitting field of this polynomial x to the power n minus a, where this n is of course that n, and this definitely is a polynomial over f. Then there are two conclusions, right? The first of which says that if we take any root of this polynomial and adjoin that root to f, then that equals k. That is the first conclusion. And the second conclusion was that the alpha group of this polynomial over f is abelian. So the first conclusion was this, that K is the extension, simple extension fu, where u is any root of this. And the second conclusion is that the Galois group of our polynomial over f is abelian. Alright. Now, how exactly are we using this to conclude this? For that, so this is the statement of that lemma 573. For that, you have to go back to the conditions that this omega i's satisfy. In particular, among all those conditions, you have this condition. Note that what is fi according to how we have the fields, according to that pattern, fi is obtained from fi minus 1 by adjoining some element omega I to fi minus 1, where some power of omega I belongs to fi minus 1. Alright. Now consider this. This element itself in place of a. We need a to be non-zero. This is non-zero because if this is 0, since we are after all in a field, omega I has to be 0 because a field is an integral domain, so it cannot have 0 divisors. So if a power is 0, then the original base has to be 0. But if omega I is itself 0, then it belongs to fi minus 1. So adjoining omega I to fi minus 1 won't give us anything new. Fi will be equal to fi minus 1, but that's not what we have in that sequence. I mean, that's a useless thing. No, if I would one attach or adjoin an element of a field to itself to get nothing new, we are, every time we are doing this adjoinement, we are getting a new field. Okay, so that's how the sequence progresses. So this is non-zero. Well, actually there is no need to say that omega I itself is non-zero, although it will be, but this itself is non-zero. Okay. Now consider this polynomial x to the power ri minus omega I to the power ri. This is a polynomial in fi minus 1 x, because its constant term is after all an element in fi minus 1. Okay. Now, if you take any root of this polynomial, any root, and adjoin that root to fi minus 1, that should be the splitting field of this polynomial. Now, this polynomial may have many roots, who knows what those roots are, but among all those roots, omega I itself is a root. So, if we adjoin omega I to fi minus 1, we will obtain this extension. That should be, according to this first conclusion, the splitting field of our polynomial. Of this polynomial means this polynomial, this one. Okay, but that extension is nothing but fi, which means that fi itself is the splitting field of this polynomial. But if you go back to a previous result, you will get then this. that a finite extension of a field is a normal extension. This is Fi is a finite extension of Fi minus 1. This is a normal extension of Fi minus 1 if and only if it is the splitting field of some polynomial over Fi minus 1. It is the splitting field of this polynomial over Fi minus 1. And that is why this is a normal extension of Fi minus 1. Okay, so that's how this lemma implies this. So that's the first thing. And because each Fi is a normal extension of Fi minus 1, and we have already seen that our assumption, that is Fk is a normal extension of F, which in turn implies that Fk is a normal extension of each Fi, further implies this. These things very quickly become confusing because we have already seen how this thing is coming, so we can erase this part and continue from here. Now, I think I myself have got a little confused. See, we first of all did what? Our assumption was that Fk is a normal extension of F. So, it will also be a normal extension of the intermediate fields. That means Fk is a normal extension of each Fi. And now we are also concluding, because of this lemma, that Fi is a normal extension of Fi minus 1. And that is why we can use the fundamental theorem of Galois theory here, which is Theorem 566. So, by Theorem 566, I am not going to write the entire statement of that theorem. You go back and see, there you will see that it directly implies this, that the group of automorphisms of Fk over Fi is a normal subgroup of the group of automorphisms of Fk over Fi minus 1. If extension is normal, then the subgroups are also normal in their relation, that one of them is a subgroup of the other. This may be a little confusing at first. The direction in which, which one is a subgroup of what, that may be a little confusing. But let's look at that like this. Fi is an extension of Fi minus 1, right? That means Fi minus 1 is a subfield of Fi. And we are saying that this is a subgroup of this. That means this is contained in this. Looking at the indices, the containment seems to have become opposite. It is opposite. But how? If you take anything here, what are the elements that we have in this group? this group has the automorphisms of Fk that fix all the elements of Fi. That means if you consider any automorphism of the field Fk and then you see whether that automorphism changes nothing coming from Fi. You take any field element from Fi, put that in that automorphism, it gives you that element back. It doesn't change it. That type of automorphisms constitute this group. And similarly for that one, now if you take, say anything, say sigma is an automorphism, that is sigma is an element in this group. So sigma is an automorphism of Fk that fixes everything in Fi. Since Fi minus 1 is sitting inside Fi, so automatically sigma will also fix everything in Fi minus 1, and that is why sigma is an automorphism of Fk which in particular also fixes everything in Fi minus 1. So sigma will be an element here. That's why the containment gets reversed. Its direction changes. That is true in general, but normality of this extension over this means that this subgroup is a normal subgroup of this. That's one thing that this fundamental theorem of Galois theory says. And now if we vary this I, we will similarly get, just like the chain of fields, we will now get a chain of groups. And then this theorem will say something further about that chain. So we can consider the following chain of groups where here also we start with F and then we consider F1, F2 and so on, but the containment will be opposite, in the opposite direction. This is the largest one that contains, that is a, do not call supergroup, we do not say anything like that, but this is the superset of this, which is in turn a superset of this, and in this pattern it goes. Finally, we also have this, and in this chain we also consider the trivial group. Why? Because ultimately we have to show that that the Galois group of our original polynomial Px is solvable. So we want to have solvability, and solvability by definition considers such a chain of subgroups. At one end of the chain we have the trivial group, that's why. Okay, so we have already said that in each each group in this chain is a normal subgroup of the previous one. This is a normal subgroup of this, this is a normal subgroup of this one is a normal subgroup of the previous one, and this of course in a trivial way a normal subgroup of this. This of course does not have any previous one, so the statement doesn't apply to that. Now additionally, theorem 566 says something else also. It says additionally this, since Fi is a normal subgroup, Fi is a normal extension. very easy to confuse groups with fields. Fi is a normal extension of Fi minus 1. It follows from Theorem 566 that now, because this is a normal subgroup of this, we can form the quotient of this by this normal subgroup, and that quotient group will be isomorphic to another group which looks like this. That is this quotient group Fi minus 1 quotiented by GFK, comma Fi. This quotient group is isomorphic to this group Fi minus 1. Okay, and here also the way Fi and Fi minus 1 appear on this side, here the order changes. First Fi minus 1 appears and then Fi. You understand why, right? I mean, this is a subgroup of this, so obviously the quotient will look like this. On the other hand, Fi minus 1 is a subfield of Fi. So it makes sense to consider the group of automorphisms of Fi that fix all the elements of Fi minus 1. That way you can remember. Okay. So this is the thing. Now, what do we know about this group? Again, we take the help of lemma 573. And now, we are going to use part 2, the second conclusion of lemma 573. By lemma 573, this group is abelian. How? Exactly in what way have we used lemma 573 so that this conclusion we can draw? Again, you go back to the situation that we had in that lemma. We already know that Fi is obtained by adjoining omega I to Fi minus 1, right? Where omega I to the power Ri belongs to Fi minus 1, and from one part of this lemma, I mean the first part, Fi becomes the splitting field of this polynomial over Fi minus 1. So, from the second part, the Galois group of this polynomial over Fi minus 1, okay, has to be abelian. But of course, this is the Galois group, because what is the Galois group? Say you have any polynomial fx in over some field f, and let k be the splitting field of fx over f. Then by definition the Galois group of fx over f is this group. So this is the Galois group, and part 2 of lemma 573 says that the Galois group of this should be abelian. That is why this is abelian, and that makes this isomorphic group also abelian. Hence, this is also abelian. Now you are looking at a chain of groups like this, where each subgroup is a normal subgroup of the previous one, and the quotients that you can form, many quotients you can form from this situation. For example, one of them is this group quotiented by the identity group, which will be isomorphic to this group. That is abelian. The previous group slash this one is abelian, because just now we have concluded that. So all the quotients are abelian, and we also have normality. This means by definition that this original group from where this series or this chain has started is solvable. This we have actually shown everything that we need in the definition of a solvable group to conclude that this is solvable. So that will be our conclusion now. I haven't further gone into more details of how the fundamental theorem of abelian group, for example, lets us conclude these things, but that is extremely easy. No, in fact, the application of lemma 573 is not immediately clear. So we have discussed that part. Hence, this is a solvable group. But we cannot stop here itself. Now note this. Since, but because it's not the f case that we are, I mean the f i's that we should be interested in. Our interest should be in the original splitting field k of our original polynomial px. Since k is a subfield of fk, k is a normal extension of, well, that's not the reason k is a normal extension. K is a normal extension of f because it's the splitting field of the polynomial px over f. What have I written here? Now, what I wrote here is wrong. It's not because of this that k is a normal extension. I mean, we have this, and along with that, k is a normal extension. That should be how I should write it here. Now, k is a subfield of fk, and k is a normal extension of f, since k is by definition the splitting field of a polynomial over f, and that polynomial is px. And that is why we are again in a position to use the fundamental theorem of Galois theory. That is Theorem 566. So, by Theorem 566, GFK comma F is a normal subgroup of GFK comma K. Have I written this one also incorrectly? Maybe, because here the order is not, no. My mind is somewhere else today. No, this is not true. It should be like this. It does not make sense for this to be a subgroup of this. This should be a subgroup of this, because you just now we have seen that when F is contained in K, then the group of automorphisms fixing K should be contained in the group of automorphisms fixing F. The containment gets opposite. And if we form the quotient group, that is this one, then that should be isomorphic to this. Yes, that's what the fundamental theorem of Galois theory implies. Okay, now what can we say from this? From this, it follows, hence, this is a homomorphic image of this group. We know, excuse me, we know that if, say, A is a group, right? So we are going back to a little group theory. Suppose A is a group and B is another group, and there is a homomorphism phi from A on to B, say. When that happens, then we say that B is a homomorphic image of A. In other words, B is an image. B is the image of A under a homomorphism. That is, B is A phi. Remembering that we write mappings on the right side, not phi of A. But we also know that if C is the kernel of this homomorphism, then the quotient group of A by C is isomorphic to B, that theorem. And that is why every homomorphic image is of the form A slash C. So that is why this quotient group is a homomorphic image of this group. But this quotient group is isomorphic to this, so that is why this is a homomorphic image of this. And just now we have concluded that this is a solvable group, which is this part of course is not a part of the proof. Which is a solvable group. Is every homomorphic image of a solvable group itself solvable? Yes. And that is our corollary to lemma 571, which we have already seen. Hence, by the corollary. There is only one corollary, so no number was given to it. By the corollary to lemma 571, this group is solvable. Finally, note that this is the Galois group of Px over F. We wanted to show that the Galois group is solvable, so we have shown that it is solvable. After this result, there are two remarks and our final result, final theorem, which however we will discuss in another field theory video, the next one. So I am stopping here itself, and tomorrow we have our usual class 11 functions. Tomorrow we will complete that section. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.